Right, this is revision of level 2 shapes of molecules. Okay, how to work out the shape of a molecule. Number one, count the number of electron sets or regions of negative charge on the central atom. Negative is important because, of course, these negative electron clouds repel each other. The electron sets repel each other around the central atom. For that, you need a Lewis diagram. Electron sets can be a bonding pair of electrons, that is a single covalent bond, or a non-bonding pair of electrons, a double bond, or a triple bond. Each of those is an electron set, and there's usually more than one of them on a central atom. The electron sets repel each other as far as possible to minimize the force between them. They get as far apart as they can. This usually makes some sort of fairly symmetrical sort of shape. The name of the shape is taken only from the atoms, or bonding sets if you like to call them that, not the lone pairs. It is the name of the 1D, the 2D, or the 3D shape that the molecule fits into. The level 2 shapes are tetrahedral, trigonal pyramid, trigonal planar, bent, or linear. And I'm going to use as my example molecules that have 4 electron sets. Rightio. So we've got some columns here. We've got the total number of electron sets, which of course is always 4. And this can actually lead to 4 different shapes depending on how many of the sets are bonding sets. So here we've got 4 electron sets in total, and for this row, 4 of them are bonding sets. Gives us a tetrahedral shape. As an example, I put down methane. So what's this tetrahedral business? Here is a tetrahedron. Tetrahedron is a solid or closed shape that has 4 sides. This one is also called a triangular-based pyramid. Later on we'll see that we have to deal with a square-based pyramid. Okay, we have to be careful because a couple of shapes here are triangular-based pyramids. Now, that shape is used because if we look at, say, for example, the methane molecule, it would fit in there with the atoms in the corners of that shape. So I'll just see if I can persuade this model to come out, cooperate. So there we have our tetrahedral molecule with the central atom. The toothpicks here represent the electron sets. And at level 3, we also want to know the angles between the bonds. And if it's totally symmetrical, the angle between all those bonds is 109.5 degrees. That's called the tetrahedral angle. And that will be the same angle between any 2 bonds in our other molecules. So if we go back with 4 electron sets and we have 3 bonding sets, we call this a trigonal pyramid, and our prize example is ammonia here. So if we draw a 3-dimensional diagram looks like that, we don't draw the lone pair. There's still 4 electron sets around the nitrogen atom, but in the shape molecule, of course, we don't show that. So if we have a look at that, then we have this shape here. This is the trigonal pyramid, and if I put it in an angle so that you can see the difference between that pyramid and the tetrahedral pyramid, which is not going to cooperate, I'll just tilt those up a little bit. You can see that although the base of the shape is the same, the triangular pyramid is a very low flat pyramid compared to the very upstanding 3-dimensional tetrahedral pyramid there. Okay, and again, if we have a look at that, because there are still 4 electron sets, you can count them there, the toothpicks, then the bond angle is still 109 degrees, although at level 3 you would possibly be expected to know the lone pair has more repulsion, as there's no atom pulling on it to pull the electron cloud a bit further out from the central atom. So that lone pair pushes that angle closed, but I think for ammonia it's around about 107 degrees between any two bonds in that molecule. The next shape with 4 electron sets, but only 2 bonding, would be a bent shape. And our prize example of a bent molecule, of course, is a water molecule. And again, you don't see the 2 lone pairs sitting out there pushing those 2 bonding pairs down, making a little bent water molecule. If those lone pairs suddenly disappeared, it'd suddenly be a linear molecule. We would no longer exist, and neither would the oceans. Funny, that little kink makes such a difference to our world. So it is a flat V shape, basically. And again, the bond angle is at approximately 109, but with 2 lone pairs pushing. For water, I believe the bond angle is around about 105 degrees. And the last shape that we want to deal with, of course, is where we have 4 electron sets, but only 1 is bonding. Here is our bonding set, and there are our 3 lone pairs there, our non-bonding sets. And you can see that the 2 atoms can only form a straight line. And for this one, of course, with 1 bond, you can't have a bond angle between 1 bond. You need a bond angle between 2 bonds. Okay. Now, that was the most complicated level 2 shape, but of course, you can now go away and make a chart for 3 total electron sets, and the shape of 3 electron sets, 3 bonding, 3 electron sets, 2 bonding, 3 electron sets, and 1 bonding, and also consider the bond angle that is always made by those 3 sets that we always have. So that is a revision of some of the level 2 shapes of molecules.